Hamilton's Rule by
Arpine, Chimayan, and
Melanie, Mikhaeilyan. William Donald Hamilton graced us with his presence in the year 1936. Unfortunately, he died in the year 2000, but has been recognized as one of the most significant English evolutionary theorists of the 20th century. And now, let's begin our lesson.
Hamilton proposed that an individual's total fitness can be viewed as the sum of two components, direct fitness and indirect fitness. Direct fitness is the number of viable offsprings that it produces. Indirect fitness is the incremental effect that the individual's behavior has on the direct fitness of its genetic relatives. So remember, direct fitness plus indirect fitness equals inclusive fitness.
Kin selection and altruism.
Kinship answers the question of why natural selection would favor an individual who performs an action that has the consequence of reducing its own fitness while increasing the fitness of another. This is known as the altruism problem. So what is kin? Kin means relatives are more likely to be genetically similar than non-relatives. Now let's discuss Hamilton's rule. Altruism is favored by natural selection when R times B is greater than C, or otherwise written as R times B minus C is greater than 0.
R.
R stands for relatedness, which is the proportion of shared genes.
B.
B stands for benefit of the recipient, which is how many more offspring are produced.
C.
C stands for the cost to the altruist, which is how many fewer offspring are produced. So how does a gene spread in the population? By favoring its own transmission in other individuals with that gene.
What is the extent to which natural selection favors assisting family members? Hamilton answered this question. It depends on how related individuals are. If we have high relatedness, a high benefit to the recipient, and a low cost to the actor, then natural selection should favor individuals who help their kin. But how related are two individuals? We refer this to as the coefficient of relatedness, otherwise denoted by lowercase r. Let's refer to these two individuals as A and B. Step 1. Locate the most recent common ancestor of A and B. Step 2. For each recent common ancestor, calculate the probability that a given allele copy in that ancestor has been passed to both A and B. And also remember, in each sexual generation, there is a 50% probability of obtaining an allele that is identical by descent. In the case that A and B share one recent common ancestor, the probability that they share an allele is 0.5 to the power of k, given that k represents the number of generations. And in the case that A and B share two recent common ancestors, add the probability that A and B share an allele through one of the most recent common ancestors to the probability that A and B share an allele through the other most recent common ancestor. And now let's calculate the coefficient of relatedness. R between full siblings A and B is 0.5. R between parent and offspring is 0.5. R between uncle and nephew is 0.25. R between grandparent and grandchild is 0.25. R between first cousins is 0.125. R between half siblings is 0.25. And R between self and identical twin is equal to 1. Genetic relatedness to existing full siblings and full parents is half of R to self. In conclusion, individuals value themselves more than they value their siblings as well as their parents' potential future reproduction. Unfortunately, sibling rivalry and parent-offspring conflict thus develop. The end.